Let's consider some reaction mechanisms that will give a first-order rate law. As we said, a first-order rate law could have an infinite number of reaction mechanisms, and we'll consider here just the simplest reaction mechanism that will give a first-order rate law. Here it is. A, which is some species, goes to products. Here we're giving products B. And it's unidirectional, only goes one way, so it doesn't make sense to talk about equilibrium for this reaction. And we're going to use the symbol K1, subscript 1, to indicate the rate constant for this reaction. K1 will be subsequent reaction mechanisms. 1, 2, 3 will indicate forward rate constants for first, second, third steps, and -1, -2, -3 will indicate reverse rate constants. But in this case, we have just a unidirectional reaction. So we should be able to go from a reaction mechanism to a rate law. Here is the rate. We're writing the rate as dA dt, and we're looking at how A changes with time. Well, A disappears because of the forward rate here, and the rate then will just be proportional to the concentration of A. The proportionality constant will be K1. So here is the rate constant. Again, since A appears just to the left of this step, is proportional to A to the first power. K1 is a proportionality constant, and we have a negative sign here because A is disappearing as this reaction proceeds. So there's the differential rate law, and here A is raised to the first power. So this rate law is first order in A and first order overall. Oftentimes what we want is not the rate law or the differential equation, but in fact we want to know how the concentration changes with time. So that means we have to integrate the rate law and get the integrated rate law. Let's go ahead and do this for this reaction. So I'll just rewrite that here. This is dA dt. That's equal to minus K1 times the concentration of A. Let's integrate this equation. We know that from introductory calculus that what one does is try to separate variables, get all the things that depend on A on this side and all the things that depend on T on this side. So let's do that. Let's divide through by A. So this will go to dA 1 over A, and we'll multiply by dt. This will be just minus K1 times dt. Now we can integrate both sides. We've separated variables, dA dt. We'll integrate this from minus, we'll do the indefinite integral here, K1 dt. So the integral of ln, or integral of 1 over A is ln of A. That's equal to minus K1t. And then we have that integration constant C. To determine the integration constant, what we'll do is say, take initial condition, say at time equals 0, the concentration of A is equal to A0. Put that in here, determine what C is. So we have the natural log of A0. That's equal to, well, that term will go to 0. That's equal to C. So that's what C is equal to. So then we can put that in there. So our integrated rate law, ln, including the integration constant, A, is equal to minus K1t plus natural log of A0. That's what C is. We can say subtract A0 here. We'll get ln of A over A0. That's equal to minus K1t. And if we take e to the both sides, we end up with A over A0. That's e to the minus K1t, or concentration of A, how A changes with time, is equal to the initial concentration, e to the minus K1t. So there's the integrated rate law, and that was fairly straightforward if we remembered integral calculus. And there is what the integrated rate law is. So the rate, first order, depends on first order, raise to the first power, integrate that. The concentration of A depends exponentially on time, e to the minus kt. So A will decrease exponentially. Now let's consider a little more complicated reaction, and let's have a bidirectional or bidirectional reaction. Instead of unidirectional, let's have bidirectional. So here A can go to B, but there's an equilibrium, so B can also go to A. So this is back and forth, and we can talk about an equilibrium constant K. K, remember, is defined as the equilibrium concentration of B over equilibrium concentration of A. That should be A there. And from our discussion in kinetics, this is equal to the forward rate, K1, rate constant, over reverse rate constant, K minus 1. We should be able to go from this reaction mechanism directly to the rate law, and here it is. Note that A is decreasing with time by the forward reaction, so this term will be for the forward reaction. But A now, in contrast to the unidirectional reaction, here A can increase with time by the reverse reaction, so B can convert to A. And so then you have a term in the rate law having to do with the reverse reaction. And note that the reverse reaction has a positive, so A changes positively with B. As B forms A, you get a positive, and A decreases concentration of A. That's why you have a negative sign there. So that's the rate law, and believe it or not, this is first order. You might think, well, it's second order and so on, but we'll show in just a minute this really is a first order rate law. And then we'll show how you can integrate here. All right, so let's look at this differential equation a little more carefully. Now for the bidirectional, dA, I'll just rewrite it here, dA dt. Well, A decreases, but A also increases, K minus 1 times B. Now, A is a function of time, A is a function of time, but also B is a function of time. Here you have two variables, both of which depend on time, but you only have one equation. You need a second equation, an independent second equation, in order to solve this equation here, which has two variables. The second equation, you can always write a conservation condition. So let's take the total amount of A, since we're measuring A. That is always equal to the concentration of A at some time plus the concentration of B at some time. Why is that? Well, if we go back to the reaction mechanism, we look at the stoichiometry. Say 1 mole of A decreases, but the concentration of B increases by 1 mole, because it's a 1-to-1 stoichiometric ratio. So there's a constant, because we've written this chemical reaction mechanism or chemical reaction, we have stoichiometric relationships. So as A decreases, B increases by just the same amount, or in other words, the concentration is constant, and the constant we'll just take here as total concentration of A. Okay, so now we have two equations and two unknowns. The two unknowns are A and B, and let's solve this. Well, since B is here, we have dA dt. Let's get rid of B here. We'll use the conservation condition. B is a total amount of A minus A, and we'll put that up into there. So we get one equation, dA dt. That's equal to minus K1 times A minus K plus K minus 1, so it should be a minus sign there, times B, but B is the total amount of A minus A. And we rewrite this a little bit. Let's, there we have, there's a minus K minus 1A, so let's write this as minus K1 plus K minus 1 times A plus K minus 1 times A total. So there's the differential equation we have to solve. And to note that this is first order. So here's the rate. The rate just depends upon one concentration, A raised to the first power. So this is first order. Even though we might have thought, first off, that A and B, two independent, maybe it would be a second order or something more complicated. But in fact, because of this conservation condition, there's a stoichiometric relationship between A and B, and therefore it is just first order. Let's rewrite this equation in this form here. Say dx dt, just simplified a little bit. That's equal to, say, ax plus b, where x we're going to associate with a concentration of A, and here we'll explicitly make the fact that it depends on time. We said A was minus K1 plus K minus 1, and B is equal to, we said, K minus 1 times A total. Now this is a first order linear differential non-homogeneous differential equation. The non-homogeneous means you have this constant term here. Because it's a first order linear non-homogeneous equation, we can't use the techniques we used previously for the unidirectional reaction mechanism first order. I'll show you why. Well, let's try to separate out variables. Dx will be equal to ax dt plus b dt. Oh shoot, there's no way you can separate x and put it over here and t and put it over here. So this implies that you can't separate variables like we did before, and so there's no easy, one or two step way to solve this equation. Now there are ways to do this, and if you look at the introductory calculus books, you can probably figure out those ways, use an integration constant and so on. But we have Wolfram alpha to help us. So let's have Wolfram alpha solve that equation. Again, what we want is how we want x, or we want x is a here. We want to solve that, so let's just write down Wolfram alpha. We'll tell it to solve this equation, dx dt equals ax plus b. Okay, so we'll ask Wolfram alpha to solve that for us. It knows that x is what we want to solve for, and a and b are constants. Okay, here it is. It solved it. We just check the input. Yeah, dx dt is ax plus b. And here is the solution down here. X of t is c1 e to the at minus b over a. So let's write down that equation. Wolfram alpha says that x is equal to an integration constant c1. You always have an integration constant if you do indefinite integrals. E to the minus at minus b over a. And let's substitute in here for that. We'll have dA dt. That's equal to the integration constant c1 e to the minus sum of the rate constants k1 plus k minus 1 t minus b over a, k minus 1 a total over a minus, so that minus and a minus will make that a plus, k1 plus k minus 1. So there is, oh sorry, what am I doing here? That is not dA dt, we're solving it for x, duh. Let's see, so this is just concentration of A as a function of time. So A will decrease exponentially with time, as we expected as a first order reaction, but we have these additional things here. Well, let's look at this term in a little more detail and see what we can say about this. So we have, let's write that term k minus 1 a total divided by k1 plus k minus 1. Let's divide both the numerator and denominator by k minus 1. This is just a total over k1 plus k minus 1 plus 1. And this we said was the equilibrium constant. So this is just equal to a total divided by 1 plus the equilibrium constant k. Now we can simplify this further by realizing we have equilibrium constant A in equilibrium with B, and we can have an equilibrium constant K for this to be defined as the equilibrium concentration of, products, equilibrium concentration of B over the equilibrium concentration of A. We know that we can rewrite the equilibrium concentration of B as A total minus the equilibrium concentration of A over equilibrium concentration of A. Why can we do that? Well, we have our conservation condition. The total amount of A is A plus B. This will hold at any time, even at equilibrium. So the total amount of A is the equilibrium concentration of A plus the equilibrium concentration of B. And therefore, we can write this equation here. And I'll let you figure this out. But what you find out is that the equilibrium, solve for the equilibrium concentration of A, that's equal to the total concentration of A divided by 1 plus K. Oh, look at that. So we can substitute that in there and simplify this equation that we had before, simplify this equation. So finally, we end up with A as a function of time is equal to C1 e to the minus sum of rate constants K1 plus K minus 1 times T plus the equilibrium concentration of A. Now let's try to figure out what this integration constant is. Well, we'll use our initial condition, say at time is equal to 0, the concentration of A is equal to A0. Okay, so we'll put that in, time equals 0, that term goes to 1, so A is in A0, so A0 is equal to the integration constant plus equilibrium concentration. Or the integration constant then is equal to A0 minus equilibrium concentration. So we have A of t, how A changes with time, that's the concentration we're measuring, is equal to A0 minus the equilibrium concentration of A, e to the minus sum of the rate constants, K1 plus K minus 1, T, plus the equilibrium concentration of A. And in general, for if you have a first order linear non-homogeneous differential equation, you can always write the solution to that. Let's use A. A will be equal to A1 e to the A2t plus A3. So the general solution to first order linear differential equation is you have three parameters, A1, A2, and A3. That's what this is, A1, A2, and A3, where A2 is the sum of the rate constants for this particular case here, or minus the sum of the rate constants. So that's a general handy thing you may want to remember, is that if you have a general differential equation like this, inhomogeneous, that the solution will be x as a function of time is exponential, and then the parameters A1, A2, and A3 can be determined by the conditions of the experiment. All right, so let's take a look at this thing here. Let's contrast and compare this with the unidirectional reaction mechanism. This equation here, the integrated rate law, is for the equilibrium, A goes to B, and before we had the unidirectional, A just goes to B. If we compare these two, if you don't have any reverse reaction, this means that K minus 1 is equal to 0 for that one, and the equilibrium concentration of A, since A completely goes to B at equilibrium, whatever that's defined as, the concentration there will be equal to 0. So with a K minus 1 equals 0 and A equilibrium equals 0, we put that in. We find that for the unidirectional, we have A minus 0 is equal to A0 minus 0 e to the minus K1, and the reverse rate was 0, t plus 0, or in other words, A is just equal to A0 e to the minus K1t plus 0. So this is for unidirectional. So this is a general case, and then if you take the specific case of where the reverse rate constant is 0, then you reduce to the unidirectional first order reaction mechanism. So let's see what these look like. Let's make a plot of A versus time. And for the case of unidirectional, A will decrease to 0. At infinite time, you'll have no A left. And this will decay as e to the minus K1t. And initially, at time equals 0, you have a concentration A0. If one does a semi-log plot, take the natural log of A versus time, then you'll get a straight line whose slope is equal to minus the rate constant K1, the forward rate constant, and whose intercept here, this is equal to the natural log of A0. Let's look at the more general case for bidirectional, where you have both a forward and reverse rate. We'll start here again at A0 at time equals 0. And this will decay to the equilibrium concentration of A. It won't decay to 0 because there's a reverse reaction. So here we have equilibrium concentration of A. And this will decay as e to the minus This decay is e to the minus k1 plus k minus 1 t. Now to do the semi-log plot, you have to plot natural log of A minus the equilibrium concentration of A versus time. Then you get the slope here, or you get a straight line whose slope is minus k1 plus k minus 1, and whose intercept here is the natural log of A0 initial concentration minus equilibrium concentration EQ. So don't be confused. You actually have to subtract off this very long time value from each concentration here, A, in order to make the semi-log plot. Let's look at some characteristics of that exponential decay. Here we'll take the general case of bidirectional. If we want to make it unidirectional, we'll just say K2 or K minus 1 equals 0 and equilibrium concentration equals 0. So here we'll plot A as a function of time, and we're going to start here at A0, and this is going to decay to some equilibrium value, A equilibrium. Now the equation for this line, A is equal to A0 minus equilibrium concentration of A, e to the minus k1 plus k minus 1 t plus equilibrium concentration of A. What would happen if time is equal to just the reciprocal of k1 plus k minus 1? Then A is equal to A0 minus the equilibrium concentration of A divided by E plus the equilibrium concentration of A. Because this term will be e to the minus 1, you just divide that by E. And 1 over E is about equal to 2/3. So what one does is look at the time by which the reaction decays by 2/3. This will be 2/3 here. This will be 1/3. This is approximate. That time there will be equal to 1 over the sum of the rate constants K1 plus K minus 1. So one just from this decay can approximately determine what the sum of the rate constants will be for the forward and reverse reactions. Let's look at, say, when when A is equal to 1/2 A equilibrium, A0 minus A equilibrium plus A equilibrium. What does that mean? That means that you're halfway down here. So here you're 1/2 and here you're 1/2. So you go halfway down the extent of this, and that time we'll call the half time, T 1/2. So that means what happens if you have 1/2 A0 minus AEQ, that is equal to A0 minus AEQ, e to the minus sum of the rate constants times T 1/2, we'll call that half time, plus AEQ. This implies that the half time, T 1/2, is equal to the natural log of 2, you can work this out, divided by the sum of the rate constants K1 plus K minus 1. So here the half time is equal to natural log of 2 divided by the sum of the rate constants K1 plus K minus 1. So this gives you another approximation. See how long it takes for this reaction to decay to half of its equilibrium value, and that time is equal to natural log of 2 over 1 over the sum of the rate constants. And a final property of exponentials, which is useful. So let's take the general exponential here. Let's say measure A versus time, and we're decaying down here like this. And we say, all right, we'll start here. That's where it ends. We'll go halfway here, and this will give us a half time T 1/2. And that time there is T 1/2. But what a particular property of exponentials is, this is like e to the minus, say, alpha t, where alpha is an exponential term, is that if you start, say, here, say that is redefining this as time equals 0, and look at the time it goes to go halfway here, this change in time delta t is also equal to the half time t1 half. That's interesting. So no matter where you start, the time it takes to go halfway down is the half time. So suppose we start here. The time it takes to go halfway down is a half time. That time, I didn't draw it very carefully, but this half time should be that half time, should be the half time, and so on. So the half time is independent of 0 time. In other words, you can just, anywhere on this exponential, you could start and then see how long it takes to go to the equilibrium value. That half time would be the same if you started at time equals 0, or this time, or this time, or this time. So the half time is independent of 0 time for an exponential. And finally, let's take some examples of the unidirectional. We said A goes to B with a rate constant K1. Some examples. This would be radioactive decay. Radioactive decay never goes reverse. It always goes one way, spontaneous. We can write this is the reaction mechanism for radioactive decay. Let's give an example. Say you have carbon-14. That decays unidirectionally to nitrogen-14 plus a beta particle plus a gamma particle. And let's write this K1. There's the reaction mechanism, so we can immediately say that the concentration of carbon-14 is equal to the concentration of carbon-14 at time equals 0, e to the minus K1t. And it doesn't matter where we measure the 0 time, this equation will always hold. And K1 then will be the radioactive decay constant. Here's another example. Suppose that we have a cell or a membrane vesicle surrounded by a membrane, and inside here we have some radioactive substance, and we're going to measure how fast that comes out here into the extracellular space. We can arrange the experimental conditions here so that the reverse reaction, namely outgoing in, is very small and can be negligible, and we do that by making the external volume, the volume of the solution outside the cell, to be very large. This means that we have this reaction mechanism. The radioactive tracer goes to one way, only one step here, K1, goes to out, which, because this is a unidirectional, one-step, first-order reaction mechanism, we can write that the concentration of the radioactive tracer inside varies with time as the initial concentration at some time equals 0, e to the minus K1t. And K1 here can be related to the permeability, the membrane permeability. So something is very permeable, you have a very large rate. So those are two examples of the unidirectional first-order reaction mechanism.